Okay, thanks guys for attending the lecture today. And today we have our third lecture of the superstructure part. So today we will be looking at the live load, and we will make a revision for some of the concepts we had last week. So please, if you have any question during the lecture, please let me know. So let's start looking at the slides. So we will continue on the structure actions, which we start last week about the dead load and live load. And in this week, we will make a quick revision and then go through to the live load. So let's start with the revision about some of the concepts we learned in the last week lecture, because these are some of the important terms and the important information we need to keep with us during the semester. So in the last week lecture, we start with the load and the load distribution and how are the loads transferred through a building. So for example, if we look at this building here, which is very simple one with a slab, and the slab transfers the load to the beams, and we have four columns and footing, and finally the soil. So for the gravitational load base, which is any load vertically applied to this slab, like our load, for example, like live load. So this load will transfer in two directions like this through the slab. The slab will transfer its load to the columns, so to the beams. So this direction will send the load to this beam here, and this beam here, and this beam here, and this beam here. So this is the first step. Then the load will transfer through the beams in this direction, for example, to the columns, and in this direction also to the columns, and similar in the other sides beam. Then the beams, after transfer its load to the column will transfer this load vertically down to the footing. Then the column, after transferring its load to the footing will distribute this load to the soil underneath the footing. So this how the load is transferred, like simple for a simple building. So the load will be transferred from slab, for example, to the beams. Then the beams will transfer to the columns. Then the column transfer to the footings. And finally the footing transfer to the soil. Because all the loads of any structure at the end will be transferred, distributed to the soil. So we need to understand how the load transferred from the building or the structure itself to the soil. Okay, so I received a message that you couldn't access the week lecture last week, the recording of last week. Have you any other student has same problem or only one? Have you tried to watch the video last week recording? And if you have a problem, yeah, I think maybe you need to log in with your UniSA credential to Banetop to access the recording. So you need UniSA account and password to log into Banotop to see the video. If you have same problem after that, just let me know. Okay. Do you have any question about the load bus, the vertical load bus? Please note that this is for vertical load bus only. Now we are starting with the vertical load bus, and after we look at the wind load calculation and bracing arrangement, we will show you how to transfer the horizontal load through the elements. Okay, so this is our first part of the revision, and again, from last week lecture, we have notes about some other terms like the weight and forces, masses, and gravity. So, what is kilonewton means? Which show us a relation between the weight and mass. So generally the weight is equal to mass times gravity acceleration g. So weight in Newton or kilonewton equal to the mass in kilogram times g. G is 9.81 meter per second squared. So this is the general uh, formula of weight, which we will need in our calculation. So you need to make sure that you know how to convert from weight mass to weight or from kilogram to Newton and kilonewton. So if we go to this slide again to revise, so this formula comes from the second law of motion, from Newton's second law of motion, which give us the formula F, or the force, generally equal to mass times acceleration. So any force equal to mass times acceleration. The mass is m, and the acceleration is a, and the force is F. Okay, but in a special case for the weight, so a is replaced by g equal to 9.81 meter per second square. So the general equation for force is mass times acceleration, and for weight, it is replaced by g equal to 9.81 meter per second square. This means that the force in newtons equal to the mass in kilograms multiplied by acceleration in meter per second square. As an example of that, if we have a footy player, for example, his mass is 102 kilogram. So if we multiply the mass times the acceleration g and divide by 1,000, this will give us 1 kilonewton force or weight. So why we divide by 1,000 again? Because 1.2 kilogram times 9.81 meter per second squared will give us a value of 1,000 Newton. Then to convert from Newton to kilonewton, we divide by 1,000. So this gives us 1 kilonewton. So generally 1 kilonewton is equivalent to 102 kilogram of mass. So 100 kilogram of mass equivalent to 1 kilonewton of force or weight. Okay. This example is example of weight of one of the players, which is around 102 kilogram. Another terms we have discussed last week as well is the unit weight and density. And what is the difference between the unit weight and density? And as you noticed in our last week class, that the materials or the construction materials are given as unit weight. So the material properties or the material weight is given as unit weight, similar in table A1 and A2 of the Australian Standard 1170.1. So we need to know what is the unit weight mean and what is the density mean, because we will need these two concepts to find the weight of the materials. So let's start with density. Density or rho is the mass per unit volume of a substance or of a material. So the formula is rho equal to mass per volume. So rho equal to mass per volume. Mass in kilogram, for example, and volume in cubic meter, for example. So if you know your mass and your volume, so you can know your density. Any substance or any material in our world has a specific rho. So for example, for water, raw water is 1000 kilogram per cubic meter. Okay, so the density of water, for example, is a fixed value. So any material in our world has a fixed value of density. So the unit of the density is kilogram per cubic meter, which is unit of mass over a unit of volume. As an example of that, if we have a timber box, the mass of this timber box is 30 kilogram and the volume is 20,000 millimeter cubed. So the density of this timber box will be the mass of the box over the volume of the box. The mass is 30 kilogram and the the volume is 20,000 millimeter cubed. So it will be 0.0015 kilogram per cubed millimeter. Okay, so this is the density. So the density again is relation between mass and volume. Okay. Do you have any problem about or any question about density? Trying to revise some of the concept we learned last week so that you have better understanding of it. So if you have any question, just let me know. Okay, any query? All good? Okay. So now, if we get to the next slide. So here we will know about the unit weight. What does the unit weight mean? The unit weight can be also defined or known as specific weight. So unit weight or specific weight of the material. Okay, so the unit weight is given to us in the okay, so that's good question from Yasser. How to convert from this one to this one here, from kilogram per millimeter cubed to gram per meter cubed. So I will add a slide here. So now we have a value of 0.005 kilogram per millimeter cubed. How to convert to gram per meter cubed. Actually, this convert only was to make the number looks better because the number is too small. This number is too small. So just to make it looks better. So how to convert from kilogram per cubed millimeter to gram per meter cubed. Hi, and this is not the live load. This is we are just revising the last week lecture, and we will after that we will start the live load. Okay. So how to make this conversion, because we need to know more about conversion during our course. How to convert from kilogram to gram. 1 kilogram is equal to 1000 gram. So to convert from kilogram to gram, we need to multiply by 1000. So this is our first step. Step number one, to convert from kilogram to gram, you need to multiply by 1000. From millimeter cubed to meter cubed. How to convert from millimeter cubed to meter cubed. It's number two. The first step is 1 meter equal to 1000 millimeter. Okay. So to convert from millimeter to meter, you need to divide by 1000. But this is for 1 millimeter only, for millimeter only. If it is cubed, so you need to divide by 1000 to the power 3. Okay, so to convert from millimeter cubed to meter cubed, you need to divide by 1000 to the power 3. So whatever the power here, you need to add it to our conversion. Okay, so if we want to convert this value to gram per cubic meter, so we will have 0.15. Okay, multiplied by 1000, multiplied by 1000, and divided by what? I think this value is need to be revised, but let's have a look on it. So now if we want to convert this kilogram to gram, we need to multiply by 1000, then divide this by, but here is a point here, we have here, uh, we have here millimeter at the denominator here. So here we have the millimeter at the denominator. So we need to divide the denominator 1 over 1000 to the power 3. So we will have 15.15 times 1000 times 1000 to the power 3. Okay. So this how to convert from kilogram to gram. I think this I will revise this unit again because this value is maybe incorrect. So just leave the value as it like it now, and I will revise and update this value. Okay. But this how to convert. So for example, again from kilogram to gram, we need to multiply by 1000. From millimeter to meter, you need to divide by 1000, and because we have it cubed, so we need to add the power 3. Okay, so this for the conversion, and then let's go back to our second concept we need to know today is the unit weight or the specific weight. What is the meaning of the unit weight or the specific weight? So the unit weight or the specific weight, we need this value because again, this will give us the weight of the material, of the construction material from table A1 and A2 of the Australian Standard AS 1170.1. So all the probabilities of the material or the weight of the material given as specific weight or unit weight. So the specific weight or the unit weight is the weight per unit volume of the material. So instead of the density was mass per unit volume, the unit weight is weight per unit volume. So the formula will be unit weight equal to weight per volume. So if the weight in kilonewton, the unit in kilonewton, and the volume in cubic meter, so the unit of unit weight is kilonewton per cubed meter. So the unit of unit weight is kilonewton per cubic meter, and we need this unit in our calculation of the dead loads of the materials. Okay. For example, if we have a block of cheese that mass equal to 3 kilogram and the volume is 3200 millimeter cubed, so the density, because here it is given as kilogram, so kilogram is mass. So we can, the density will be 3 kilogram or the mass over the volume or divided by the volume. This give us this value 0.009375 kilogram per millimeter or 0.93575 gram per millimeter. So here, how to convert from this one to this one quickly? So we have 0.009375 times 1000. So this one is correct. So it has become 0.9375 gram per millimeter cubed. So to convert from kilogram to gram, we multiply by 1000 here. So this for the density. For the unit weight will be equal to weight over volume. So we don't have the weight ready for us. So the weight will be mass times the gravity acceleration g. So this is our weight. So 3 kilogram as mass times 9.81 is gravity acceleration. So this gives us the weight of this block, which is, for example, 29.43 Newton. Okay, so this is the mass. Sorry, this is the weight, which is the mass times acceleration. Okay, so if we divide this over the volume, so this gives us the unit weight is 0.0092 and the unit is 9 divided by millimeter cubed. Okay, so this is the unit weight and mass, unit weight and density. So the density again is 0.9375 and the unit weight is 0.0092. Okay. Do you have any question about the mass and the unit weight? Okay, so now we have revised the concepts, the density and unit weight, and now we can revise the concept of loads. So the loads, we have two or three forms of loads. We have actually three forms of load. The load can be point load or concentrated load. What is meant by concentrated load? Concentrated load means force that apply at single point along the structure member. So for example, if we have beam, so the load will be applied only on this point at point A, for example. So this is our load. Okay, this similar to this example of one like trade, like doing some maintenance or some cleaning on the roof. So this will applied as point load at this point of the roof. Okay, so this force or this point load is zero dimension, means at point, and this means that the unit of this force can be Newton or kilonewton. So for point load, the unit we're using are kilonewton or Newton. So this is the unit we are using. And as you can see here is the example, we have point load applied at a certain point here, and this is our beam. So this is the first type of loads we can have in our structure design or structure analysis. The second type of loads is the uniformly distributed line loads or UDLs. So the uniformly distributed life load, it is instead of the load distributed, or sorry, the load applied at a point, here the load will be distributed over the whole length of the beam. So this is called UDL. And because the beam is not an area, the beam is only a line, so that's why it's called uniformly distributed line load. Okay, so what is meant by line load or uniformly distributed line load? It means that we apply constant or equal force per unit length. So if this our beam, again, this example, so this is the length of the beam. So we have same value of load along the beam. That's why it's called uniformly distributed. So we have constant force applied per unit length of the beam. Okay, this is common in our structure analysis design of beams and columns. So when we design beam and columns, we might need to apply the load as uniformly distributed loads. So the UDL formula is force over length. So if our force is, for example, Q, so it is Q over L. Force in kilonewton and length in meter, for example. So what is the unit of the uniformly distributed line load? Kilonewton per meter. So for point load, it was kilonewton and newton. Here it can be kilonewton meter or newton by meter or newton by millimeter, but it is force over a distance, force over a distance or over a length. So this is the uniformly distributed line load. The third type of load we have is the uniformly distributed area loads or pressures. So on some elements like slab, for example, if you can see here, this is a slab or a roof. So the roof or as the slab is area. So the load is distributed over this area like that. So any point of this roof has same value of the load, which is our uniformly distributed area load. So the difference between line load and area load, that the area load is distributed over area. But here in the line load, it is distributed over a line. Okay, so line and area, this is the difference. So the uniformly distributed area load, or we can call it pressures, is a constant force applied across an entire surface area. So any point on the area, as I show you, will have same value of the force, and it can be expressed as force per unit area. So the pressure formula is force by area. Force in example kilonewton and the area, for example, in meter squared. So the unit will be kilonewton per meter squared. And kilonewton per meter squared is equivalent to kBA or kilo Pascal. Okay, because in the standard they are using kBA some cases. So kBA and kilonewton per meter squared are same. So either of them are same. So do you have any problem with the different type of loads? So we have again three type of loads: point load, uniformly distributed line load, and uniformly distributed area load or pressures. Do you have any question about the loads types? Or sorry, the loads configurations? No? Okay, so let's continue. Here is also a revision. Thank you, Max. So there is a revision about the some of the action around us and their effects. So some of what is the actions mean or the loading mean? The action or loading mean any set of displacement or forces acting on an element or structure. So any displacement or forces applied to element or structure, this is considered as an action. For examples, weight or wind pressure or earthquakes or ground movement. So if you look at this figure here, as you can see, the actual the actual electricity pole was something like this. Then due to wind, what happened due to wind? This ball has rotate and has some permanent deformation, and it's already considered as failed. So the wind is sort of the forces that can be applied on the our structure, and also earthquakes. For example, if you have a building and due to the wave movement or the earthquake waves, so these forces will push the building and make it, for example, uh, rotate, sorry, or like inclined in this direction and in this direction. So it move like up and forth, back and forth, sorry, during the earthquake load. So the earthquakes and weight and wind pressure and the ground movement are all examples of the actions that we may have on our structures. The action effect or what happened due to the applied actions, internal structure effects caused by action. So, for example, if we have a beam and we have applied load similar to what you learn in structure 1, so this beam will be under bending moment and under shear. So we have bending moment, we will learn this later, but we have internal bending moment and internal shear. These are what is meant by action effect. So the bending moment, axial force, and shear force diagram, we can call them straining actions, or the internal forces inside the members due to the forces, the applied forces. Okay. The last term we should know is the design actions, which are the values of action estimated for evaluation of performance before construction. So the design action, we will take them from the training action. So the training action will be used as the design action, but with some modification. Because sometimes in the design, you need to take a margin of safety. So the margin of safety will push us to maybe increase the string action a little bit to account for any uncertainty of the design. But our base of the design action will be from the string action. So these are the action and the action effect and the design actions that we need to consider. And if we revise what are types of actions we have quickly, so what are type of actions we have for our structure? So the first one is dead load or permanent actions. We have already go through this last week and also during the class. So if you remember, the dead load G are or are permanent action like self weight of the members. Like for example, in the class we have found the dead load of the boarding, the like particle board flooring, and the joists and the bearers. So which is the self weight of the members. Another type of load is the live load or superimposed actions or imposed actions, like similar to this one here in this diagram, which is in the standard called Q. So Q is the life load, which include people life load, furniture life load, and any load that can move on the structure is considered as life load. The difference between life load and the dead load will remain on the structure, doesn't move, and it is on the structure as long as the structure exists. But life load can be there and can move as well. So the life load can move. For example, the life load on the class floor. For example, if you are in the class, so the life load exists. If you are not there, so the life load doesn't exist. Another type of load we will consider in our course as well is the wind load. So wind load similar to this image here. So the wind loads are horizontal loads that affect the structures. So we need to consider it and it takes the symbol W. We will use the Australian standard AS4055 to find the wind load, which is wind load for housing. We have also earthquake loads or E, similar to here. So actually, when the wave of the soil come, so it makes shaking of the footing. This shaking of the footing cause some lateral forces on the building. So this will affect the building, so we need to consider it. But this one is not in our scope this year. So this one our scope, this one our scope, this one our scope. The others are just to know about, not included in our calculation. Another type of load is snow load or S. In some states or in some countries that are that have snow in winter, so we need to consider the weight of snow resting on roofs in winter and need to be included in your design. Temperature load, something similar to here and here. As you can see, due to high temperature, some extraction and contraction may happen to the element, so we need to consider this one. Another type of loads, which can be considered as live load but not in our scope, is the live or loads during the construction. So, for example, here in this photo, we have an equipment that rests on the roof just to help to to get some materials on the roof. So it is like a crane that will take the heavy material from the earth or the surface downside to the roof. So this all are some types of loads that we can deal with in our designs or our construction. So we need to consider in design. The first type of loads we learned or we started learning about last week is the permanent actions or dead load G. The dead load G or the permanent action are given or can be determined using section 2 of 1170 or AS 1170.1, the Australian standard for loadings. So the permanent actions are the forces caused usually by the self weight of the structure members. So any structure, like for example, the first one we mentioned today, the first example, we have roof, we have beams, we have columns, right? So slab or roof and beam, column. So the weight of all this member is considered our dead load. So because this is this elements or this bodies has weight, so we need to consider this weight. Who will carry this weight? Our structure. So the structure carry itself first, then carry other loads like like wind load and the life load. So again, the dead loads are self weight of structure. Any other structure members like cladding and any permanent partitions like walls and any permanent equipment that will stay forever on the floor, for example, like and any fixtures or fittings of pipes and so on, any machinery or wiring or air conditioning and so on. So anything that you think it will stay for a long time on the building should be considered as dead load. And then again, the dead load is load that doesn't move on the structure. So any load that doesn't move can be considered as dead load. Or in other terms, we can call it as the dead load are always there as long as the structure is there. So the dead loads is any load that always there and will stay as long as the structure is there. Similar to, for example, this photo and this photo. If you can see, we have the piers or girder or beams, and we have purlins. We have the sheeting itself and any other structure elements can be seen in the photo. Okay, any question about dead load and what is considered as dead load? No? Or good? Okay, so if we continue, what are the feature or the characteristics of the permanent actions or the dead load? So the characteristic of dead load, we have two or three types of dead load that we can be considered. So we have some known dead loads like most manufactured building material. So for the building material, we can know an exact value of the dead load or the weight, and the standard 1170.1 tabulates the densities and unit weight for common building materials, like in table A1 and table A2 that we used last week to find the weight, for example, for the timber material, radiata pine. So the dead load of the material or the self weight of the material can be found in this two table of the Australian standard. Other dead load that we cannot know exact value, but we can assume or estimate the values using the densities and dimension and moisture content that may vary. For example, some type of timbers here in Australia has different value of the moisture content, so the value of the unit weights are not very exact. So there will be some margin of errors, or you can do some estimation about the weight using the dimension and the weight of the material you have. And we have other dead load like permanent that stay for longer duration. So this can be also estimated based on the experience. Okay, so mainly we are working in our course about the known material or the common manufacturers materials that are available in the market, and we have an exact information about the weight of this material. And here is a table example from table A or appendix A, table A1 and A2 of the Assurance Standard 1170.1. These tables give us the unit weight of the material in the market. So for example, for concrete, for example, if you are designing a building of concrete, if it is unreinforced, so it is 24, and if it is reinforced, so you can add a value of 1 percentage for each, sorry, 0.6 for each 1% of reinforcement. Another material, for example, if you are using fiber cement sheet for walls, for example. So you have some values of it if depend on the type, compressed or uncompressed, or fire resistance or insulating sheeting. So we have this four values based on what is the material type you used. So this table give us the unit weight of the material. As you can see, what is the volume, what is the unit, sorry, for this material unit weight, kilonewton per cubic meter. So the unit weight in table A is kilonewton per unit meter, per cubic meter. And another types of material are given in table A2, for example, for ceiling or floors. So for example, if we have a ceiling of gypsum plaster, 13 millimeter thick, the unit weight is given as 0.13, but here the unit is kilonewton per square meter. So table A1, kilonewton per cubic meter, table A2 for kilonewton per square meter. Why is this table with kilonewton per square meter? Because as you can see here, here in this table, the standard give us for specific thicknesses. So if you can see, all the materials are given for specific thickness. That's why it is given in kilonewton per square meter. For table A1, there is no specific thickness. That's why it is given in kilonewton per cubic meter. So in some material, we will use table A1 and other material like plaster boards or ceiling boards and floors and so on. It is given for a specific thicknesses, so it is given to us as kilonewton per squared meter. Okay. Do you have any question about this, about the dead load? Any question, guys? Okay, thank you, Syog. Okay, now let's, and here are some other resources for calculating dead load. For example, the first one, have a look on this one and this one. This one we will be using from next week or this week, sorry, in the class this week. So these two are the sheeting or roof sheeting weight and the Berlin's weight. Okay, so if I click one of these links to show you, Can you see the screen? So this file is the weight of the roof sheeting and wall sheeting, for example, from like that. So, for example, here you can see here is some of the sheet profile we can use from the market. So any of this one can be used for a shed, for example, or a warehouse or a residential building. And as you can see here is the mass. So the mass of each one is given in this table or in this column. So for example, if I use clay block 406, the mass of this one is 5.56 kilogram per square meter. So this file or this table will give us the weight or the mass of the sheeting, and here also other types, and here is the mass. So this table, oh sorry, this file will give us the weight of the sheeting, for example. The other one of the Berlin, so if we open this one, so this file is a little bit bigger. So I have a copy of it, so I will open it. Okay, so this one is for Berlins and Gertz. So also this file give us some of the weight and the profile of the Berlins. So as you can see here, here is the Berlins. The Berlins can be C and Z, as you can see here. And the table give us the size of the Berlin. For example, this one, for example, like Z or C 250/19. The mass of this one is 6.5 kilogram per meter. So these two files will help us to find the weight of Berlin and sheeting because we will need them in our assessment and our class problems this week as well. So these are two important files. You can have a look on them. So just click the link and they will download directly. And do you still have any problem with the standard before we proceed? Yug, I think you mentioned last week that you couldn't print. Have you been able to print the standard? Or any of you have tried to print them? Okay, so I will email okay, so I will email the version, the two or three files we need from the standard to you by email so that you can print them. Okay? Thank you, Chuck, for reminding me. And if you have any problem, guys, just let me know, and I will try to help it for solve it for you. Okay, thank you. So now this is our new part of the lecture, which is the second type of load we have in our structure, which is the imposed actions or life load. The life load Q takes the symbol Q, so G for dead load and Q for life load. The life load Q is something similar to here in the library. For example, the weight of this uh, person, so this considered as life load, so it is people, and can be also also the books. Okay. Here, for example, are the goods or the stuff here. For example, a shopping center or any sort of selling shop. And here we have also some people and cars and some other brands and so on fluid. And here also we have some like goods and stored stuff like storage. So here is a library. So the weight of the books and the weight of people visiting the library is considered as live load. In a shopping center, the stuff in the shopping center can be considered as live load, or something like event or this expo can be considered also as live load. These images and the live loads are any forces that are caused by intended use and occupancy of the structure. So the live load is depending on the usage of the building. Okay, and these loads are moving on the structure or can move. Let's make it can move instead of moving. Can move on the structure. Does this mean that the live load can exist and also cannot exist based on the usage of the structure? So, for example, if you are in a school, different from a house, different from a library, different from a hospital. So this is what is meant by intended use of the building or the structure. So some buildings, the life load considered low, and some buildings and some usage of the buildings considered high. And some example of this life load is the people or crowds and storages or storage buildings or storage areas and temporary partitions and furniture. So the furniture also can be considered as life load. Weight of machineries, if the machinery is not existing for forever, so it can be also considered as life load. Traffic loads, for example, if you have a bridge, whatever the bridge is. So traffic loads means any cars, for example, passing through this bridge. So this is considered as traffic load. So the traffic load is also type of life load. And what else? Any applied load during construction, similar to the photo we have seen earlier, when the crane was on the top of the building to put the heavy weights on the or the heavy material to lift the heavy material to the roof. Here in this image, for example, we have a library again. So the books and the bookshelves and people inside the building is considered as life load. Here, for example, in a shop, so the clothes and the stuff and the desks and people also considered as life load. So the life load again, any load that can move on the structure, and it might be there and might not be there. Maybe there and maybe not there. But the dead load will be always there. So this is the major or the main difference between dead load and live load. For the imposed action or the live loads, Q, we have known values of the live load, or some of the live load we can know their values, like weight of the machines or fixtures supported by manufacturers' data, like cranes and air conditioners and so on. So again, similar to the material dead load, the manufacturer's data give us exact values for some of the fixtures weight or machine's weight. Some storage actions for racks rated for a given load. So for also the storage, the racks or the shelves, we can know how much is the weight of this racks. Construction actions for a specific lifting operation, similar to here. So for example, the weight of this crane is known for us, and also the weight lifted by the crane is known for us. So this is a known life load, or we can have a specific value for the life load. Some other life load are not exactly known for us, so we need to make estimation of the load. Reasonable, reasonably estimation, or estimate reasonably. So for example, the occupancy, based on the occupancy of the building, like weight of people and furniture. For example, if you are designing this house, so you will design the house for a number of or a value of life load. This value depend on estimation. For example, the normal days, there are family of 4 or 5 people living in the house, but in some cases, these people invite other families or make a party in the house. So the life load is not exact value, and it can change due to any unexpected event. So you need to make sure that your estimation is covering if they have any other activities different from the actual value. Okay, so that's why we can mention this is estimated value. Another thing is construction and maintenance load. So during construction, like the form works, for example, and the maintenance work. So during the maintenance and during the construction, we can have some unexpected loads or live loads. So we need also to make a good assumption or good estimation of this load during the construction. Okay, so the imposed action and live loads are given to us in table 3.1 and table 3.2 of the Australian Standard 1170.1. So 1170.1 will give us dead load and live load. Dead load in table A1 and A2, live load in table 3.1 and table 3.2. So the table 3.1 and 3.2 tabulates the imposed action or the live load for most types of building, such as schools, hospitals, library, housing, offices, labs, and so on. So every type of building you are designing will have different life load based on the usage of the building. So you can't just use a certain value of life load for all the building. For example, school will be crowded with student and families, for example, and teachers. So the life load of schools is different from the life load of a house, for example. Hospital, for example, is different from a library. So every type of building will have a certain value of life load given to us in table 3.1 and 3.2. What is the difference between 3.1 and 3.2? The difference is here. So 3.1 is for floor actions or for floors. If you are designing a floor, so you need to go to table 3.1. If we look at this table, for example, if we have a self-contained dwelling, so if you are designing a general area of this dwelling, so how much is the life load? 1.5 kPa. So we are only focusing on the uniformly distributed action in kPa, which is 1.5. So Q equal to 1.5 kPa, for example, for self-contained dwellings. Okay. Another structure, for example, for communal kitchen is 3, for example, so it is doubled. And the list has all the types, so this will be different according to the usage of the building. So the usage of the building is here, specific use or usage of the building, and based on that, you will select what is the value of life load should be applied to this building. So the life load is very simple compared to the dead load because it is directly from the standard based on the use of the building. Okay, so this was for roof, sorry, for floor. For roof, also the standard tabulates the imposed action for most type of buildings such as school and so on for roof. So table 3.2 will be for roof. Table 3.1 will be for floor. In our assessment, we will have roof and floor. So you should be careful when you use this table. This table is for roof and this table was for floor. Okay. So for example here for roof, we have two types. We have street awnings and other roof. For example, if we have street awnings, so accessible from adjacent windows, roofs, and or balconies, so it can be taken as 1.5. For other roofs means inaccessible roof. For example, if you are if for a warehouse or a shed, okay, this roof is not accessible for people. No, people will not use it, but maybe one person go up to clean or maintain the roof. So that's why we are using a minimal value here in this formula here. So the life load for inaccessible roof will be 1.8 over A plus 0.12, but not less than 0.25 kPa. So the value is very small, up to 0.25 kPa compared to 1.5 here or 3 here. So it is very minimum life load. We will know later how to find this one, maybe in the class this week, how to apply for in this formula. But this generally what is the life load for roof and what is the life load for floor. Okay. In here in this one we have mentioned street awnings. This is an explanation of what is the street awnings mean. So the street awning means similar to something like this. This is a street awning. So it is like covering a part of the street to be used for example, cafes or any other use. So in the top of that, people may be in this building or in this building can use this roof. So it is roof for the people under it, and it is floor for the people on top. So that's why the life load of street owning is high life load because it can be accessed. So the awnings means covering that like a roof or extended from a roof and can be used as a floor as well. So this is the awnings and just explanation of the term, but we actually not using it in our design or our course. Okay, so do you have any question about the life load for roof or floor? Any query? Is it simple? Is the life load simple or do you have any problem with the life load? Okay, thank you. So now we will have a quick example about live load. Have you seen this example before? This is the same example we used the did load in the class last week. So we will use same example here to find how much is the live load on the same floor. So it is required here to calculate the imposed action on the internal bearer of this floor. So we need to find the live load on the internal bearer. Where is the internal bearer? Here is our internal bearer. The spacing between the bearer are 2.4 meter, 2.4 meter. The length of the bearer is 3.6 meter. We have particle board is boring. We have joists. And here the distance between or the spacing of the joists are 450 millimeter. So this is all the information given to us. The requirement is to find the imposed action or live loads on the internal bearers. The given floor is part of a self-contained dwelling. This information is to find live load based on use. So the use of the building or the floor or the roof should be given to you to know what is the live load from the standard. So now if we look again to the bearer, so the bearer is a line member. So if you look at this bearer outside, so this is our bearer. The bearer length is 3.6 meter. So it is a line member, therefore the dead loads and live loads should be calculated as load per unit length of the bearer. So we should find the load as uniformly distributed load in kilonewton per meter. This is what we have done during the class last week. So the same concept, but much easier. So again, for the bearer, each bearer has will take a part of the roof. This part will be, or the floor, sorry. This part will be half if this is the bearer axis. So this distance will be divided to 1.2, 1.2. So it will take half from this side and similarly half from this side. So it will take total of 1.2 plus 1.2, which is 2.4 meter. This 2.4 meter is the bearer load width or the load width of bearer. Okay, and this area will be, if we take this area out, so this area is the tributary area of the internal bearer. How much is the dimension of this tributary area? 2.4 times 3.6. So the tributary area is 2.4 meter times 3.6 meter. This is the load width and this is the bearer length or span. Okay, so same concept we used in dead load will be used in live load. Okay, now we need to find the live load on the flooring. This is the first step. How to find the live load on the flooring? We need to go to table 3.1 in the standard 1170.1. So why table 3.1, not table 3.2? Do you have idea? Because we are studying a floor. So because this is a floor, so we should study or get the value from table 3.1. So if we go to table 3.1 in the type of the structure, domestic and residential activities, so we have self-contained dwellings. So we have under contained dwellings, we have general areas, balconies, stairs, non-habitable roof. So this is not non-habitable roof and not a stair, not a balcony. So we can consider it as general area or private kitchen or whatever. So the only thing, because we don't have enough information, so we can consider it as general area. So how much the life load on the flooring? 1.5 kPa or 1.5 kilonewton per square meter. So again, the unit here is kPa. Okay. So this means that on this area, the life load on the whole area will be how much? 1.5 kilonewton per square meter. This is the life load. We get it from the table 3.1. So it is very simple. Go to the table using the specific use of the structure you have. So it is self-dwelling or self-contained dwelling. So it is 1.5 kilonewton per square meter. So this is the first step. The second step is we need to convert this load to align load in kilonewton per meter of the beam. This is similar to what we have done in last week. So we have got the life load for self-dwelling as 1.5 kPa or 1.5 kilonewton per square meter, but we need to convert this to align load on the beam. So we can have two options. We have done the step by step in the dead load. Here we can use another formula, which is the life load on the internal bearer equal to the life load in kilonewton per square meter times the load width of the bearer. So here, this life load is distributed over the whole area. Okay, so we need to convert it to align load here. To convert it to align load here, we need to multiply by the width. So if we multiply by this width, which is called load width, we will convert it from area load to line load. So this is a line load, this is area load. So to convert this 1.5 to line load, we will multiply the life load, which is 1.5 kPa, times the load width. What is the load width of the bearer? Again, if this our bearer, so the bearer will take half on top, half on bottom. So it will take this hatchet area. Is the tributary area. So the load width of this area will be 2.4 meter. 1.2 and 1.2. So total is 2.4. So now the life load in 1.5 times 2.4 meter give us a value of 3.6 kilonewton per meter. So 1.5 kilonewton per square meter times 2.4 meter. Meter go with the square, so we still have kilonewton per meter. And the value will be 3.6. So this is how the life load will look like. And the unit is kilonewton per meter. Okay. So this is how to find out the life load on a beam. Do you have any question about that? Thank you, sir. So if we summarize what we have done in this problem, so for example, in the class, we have found G equal to 0.728 kilonewton per meter, for example. This is our dead load calculations. And for live load, we have already Q equal to 3.6 kilonewton per meter as live load. The span of this beam is 3.6 meter. The span or the length of this bearer is 3.6 meter. Okay, so now as you can see, we got the two loads in kilonewton per meter. So can we add them together? Can we now make any combination or any addition to dead load and live load, G and Q? Can we add them? Yeah, they have same unit, so you can add them together. So that's why we need to find the loads in kilonewton per meter for beam. All loads, including dead load, live load, and wind load on beams should be in kilonewton divided by meter, so that we can combine them together. Okay, so now we can have found the G dead load in the class, and we have found live load in today lecture, and the live load is also distributed over the line or over the beam. So this is what we are looking at. So do you have any question about this one? Any question about today's lecture about the dead load revision and live load? No? Thank you, Syok. Okay, thank you. That's it for today's lecture. But before we go, I just want to show you the assessment. So I will open the lecture. Try to open the course website. So if we go to assessment, you should have finalized the groups today. Hopefully, most of you have assigned the groups. So for example, here, this group, I will not accept guys more than 4. So any group with 5, I will move one of the members to another group. Because we mentioned already that we have a limit of 4. So some groups has already exceeded 4. So any group with more than 4, I will remove one of the student to another group. So for example here, group 1, the limit is 4 and it reach 7. So 3 of this group will be moved to another group. So please try to finalize the group names today. The people who didn't join a group yet, so maybe 20. And for Ali Haider, he sent me email to join a group, so I will add him to a group. But any other group that exceed 4, I will move the extra people above 4 to a different group. Okay, so this is about the group, and after the group finalized, I will add like Excel or table file with the group names, final group names, so that you can contact each other and try to work on the project. And I have released the project details, so I will show it with you now. So if we look at the assessment details, as you can see, so structured projects, we have two parts of the project. The project in total is 35% of the whole grade. So you can, this is 35% in total. So 50% of it, which is 17.5, is part 1, and 17.5 is part 2. and here is the due dates of the project. And part one will be only a written report, like uh, like written report documents. So Word file, we need the Word file for this submission. And part two will be the complete report and space gas file, because we will run the model on, or model the structure on space gas. And the presentation. The presentation will be held in week 12, in the class in week 12. So we will make also timeline for the groups to present. Each member of the group should present at least 2 minutes, and the total of the group is 8 minutes based on group of four. So these are some aims and objectives of the course. You can have a look on them. So I will show you uh, the project description. So the project description is particularly focused on developing an understanding of the load bases and design process. So our focus is the load base, how the load transfers through the members until reaching the soil, and some specific design procedure for members like beams and columns. So our report will focus on the design of beam and columns. No other design of footing in this assignment, or design of bracing or Berlins. To complete this assessment, you will be required to prepare a written report that explain a practical problem. So we need a full report. This report should be like introduction and list of the cover page, table of contents, list of figure, list of table, and so on, and the body, and then references and or reference list, and so on. So full report. And we will have a presentation in week 12. So we will prepare like PowerPoint, and we will present that in week 12, in the class in week 12. The presentation should cover both parts of the project and explain your findings and evaluation of the knowledge gained through the report. Okay. The project extends, so the project will involve the following tasks. The detailed will be in the marking guide. So this is just some key elements of the requirements. So we will identify the potential loads on the shed, which include dead load, live load, and wind load. Understand how the steel structure connected. So we will have a discussion about steel connections. Load bases for vertical or gravitational and horizontal load bases. Wind load calculations. Design loads for members like dead load and live load and wind load. And draw bending moment and shear force diagram manually and using space gas. Design of beam and design of column. So the two main parts are design of beam and design of column. But to reach these two, you need to find all these three requirements. Some of the element or abbreviation used, UB is for universal beam, which is the cross section used for beam in the Australian market. UC is universal column. G is dead load. Q is live load. These are not included in our assignment requirement. So no connection design, no bracing design, no Berlin design, no footing design, and no earthquake design. So only design of beam and column. This is the design of members included in our calculation. So for the design parameters, we have some parameters common for all the students, like this one, the overall shed. And before we go through this, I will show you the shed. So this is our shed. So we have plan view and elevation view of the shed. So the shed is 2 bays. Each bay is sorry, this should be 6 and 6. I will update this one. So the total is 12, and the span is variable. So the span is variable for every group will have different span and different height. So this is how the shed looks like. So we have one frame, two frames, three frames. This is the frame elevation. The short column is half of the long column. The roof pitch is 5 degrees. This beam B2 is S over 2, half of the total span. So our focus will be on beam B1, column C1, beam B2, and column C2. So we are not designing all of them, but we will calculate the load for B1 and C1 only, and we will design B2 and C2. Okay, so this is general view of the shed, and all the parameters needed during the calculation so will be given in this two parts here. So we have span of the shed given based on your group. So see table 1. If we go to table 1 at the end, so based on your group number, you will have span and height of the column and wind region and wind terrain category. So for example, if you are group 2, your span is 8, your height is 5.75, your wind region is B1, and wind terrain category is 2. So each group will have different values so that we can differentiate, not copying or not using same file for all groups. Column C2 height is given in the table. The base basing is 7, so the overall sheet should be 14. So I will just update this one. Sorry. So 7 and 14. They're all this in yellow are for all the groups. This one also, all the groups, the life load will be same. So office office storage space from 1170.1, similar to what we have done today. For wind, the wind region is given in table 1. The wind terrain category is given in table 1. The shielding for all the groups will be no shielding, and the topographic effect will be same for all group, which is T3. So some elements or some parameters are fixed for all groups, and some are changed for depend on your group number. The roof sheeting will be Lyset spanning 0.48 millimeter. We will find it in the file I show you earlier. We will also go through this during the other lecture and the classes. I just try to introduce it to you now. The Berlin is not given, so we will assume a reasonable cross-section for the Berlin. We are not designing the Berlin, but we need to assume a section for it from the table or the file I show you earlier today as well. Berlin spacing needs to be calculated and also ensure the spacing is within the relevant limit for roof sheeting. We will know about this in the class tomorrow. Ceiling and insulation and the flooring are not given to you, so you need to make your own research to find the value. So for example, if you need a ceiling, if we go back to the dead load table, for example, just to give you an example. So for a ceiling, for example, here you can find, for example, assume fibrous plaster 10 millimeter thickness. So you can assume based on what the information you have or make your own research. Column and rafters. The columns are fixed to the footing, so fixed at the bottom. All connection for B2 are bent. Connection between rafter B1 and external column are rigid. So this will show here. Can you see bin B2 is bin connected to the columns, but B1 is rigid connection. So and also the footing is fixed. This will affect when we are designing the column. So we will use this later as well. Model frame using space gas. So we will model the frame on the space gas. We will also do this in the lecture, one of the lecture later this semester. Once we have input the frame, so we need to draw the bending moment diagram and shear force diagram and deflection using space gas. We should get the maximum value of bending moment and shear and deflection to design B2 and B1. Okay, so this will also be our one of the requirement. Here are some of the standard and some of the table we will be using during our calculation. So 1170.0, 1170.1, 4050 for wind, 4100 for steel, like design of beam and design of column. We will also use the design capacity tables for roof sheeting and Berlin to find the mass of the Berlin and mass of the sheeting. We will use the design capacity tables from Stellarian Steel Institute to find the cross section for beams and columns. So this is just general discussion about the files or the documents we will be using through the project. The design loads we have in this project is only dead load and live load and wind load. For wind load, we will only calculate the net pressure for general areas only. We will refer to that when we design the wind or find the wind. We will have load cases and load combination. Load combination means how to combine dead load, live load, and wind load together. So this will be according to 1170.0. Concrete fails. So we have two images about concrete. So you can just give us what is the problem or what is the issue in this concrete and how to avoid or fix this issue. So this will be related to the lectures you will have in week 5 and 6 by Tom Ben. And then we will have here, as you can see, here is the design, is the report. So this is the report. So the report need to include cover page, table of content, figures, list of figures, introduction, and the main thing here in the report, we need to make sure the calculation are typed or typed, yes, and the units are presented. And the main thing is to make sure that the units are consistent, otherwise the results will not be correct. Diagrams can be diagrams can be drawn manually, like by hand, or using any software like Revo or Word or AutoCAD. Any software you want to use can be used. You need also to provide a discussion and justification of the chosen design, so you can comment on your selection for beams and columns. And finally, conclusion and recommendation and reference list. So the reference list should be presented at the end of your report. Otherwise, this will be considered as plagiarism or academic integrity issues. So I need to provide a list at the end of your document. For the oral presentation, using the report, you will prepare a presentation from, for example, PowerPoint, and we will present it face to face in the class in week 12. So 8 minutes per group. So we will make a table for the groups. So each group has time to present in. So the presentation can follow this instruction like explanation of the summary. So just to briefly introduce the elements and concept you and the result you get in the report. And here also another some information or some instruction about the report, about the line spacing and font size and so on. You can have a look on that. And here are some links that can help you to produce your report, like the report writing guide and Studiosity and EndNote guide. So all this can help you to produce a good report. And here are the marking guides or the details requirement of each part. So the first part is 17.5. These are the requirements. So the first part will be only about discussion about dead load and about the loads generally on the shed, and only dead load B1, dead live load B1, wind pressure on B1 and C1. So no design in stage 1 or part 1, only loading and some discussion question like bracing layout, load base, concrete fails, and connection and steel structure. So this is part 1. Part 2 will be the remainder of the project, which is dead load live load on B2. So we will design B2 and C2 and make the space gas model and select a suitable section for B2 and C2 and the discussion. And we have 3 marks for the oral presentation at week 12. So all of this is 17.5 marks, and the first part is 17.5 marks. So total is 35 marks for the report. Okay, this is just a brief introduction of the assessment. So uh, please like finalize the group forming this week or hopefully today, sorry. And then I will post the latest or the final group names by the end of this week. Okay, and also you can start working on the project from now if you want, or maybe after the class tomorrow. So you can at least start preparing for the report and start working on the dead load and live load for the beam B1 and column C1. Okay. Do you have any question, guys, about the assessment, or do you have any question generally? Do you have any question, guys? No word limit joke. So this is just like a guideline for how much is the word limit, but no much weight on the word limit. So it can be less. So this is just the maximum word limit can be expected, and we have also 10% up if you want. But generally, just focus on the calculation and the discussion, and don't put much attention on the word limit. Okay. Any other question, guys? What part of the assignment matters the most? So the calculation or the discussion? The calculation. So the calculation is the important part because in the final exam, our final exam will be mostly calculations as well. So the calculation is important in our course. But for example, in the first part, we don't have much calculation. The most of the calculation are focused on the second part of the assignment. But in the final exam or the exam, it will be question about how to design beam and column. So it is good to be familiar with how to design the beam and column to pass the exam or to get high grade in the exam. Any other question, guys? Do you have any other questions? No? All good? Okay, guys, thank you for attending the lecture today. And if you have any question, just let me know. And see you next week. Thank you.